Look closely at the trailing edge of an airplane wing, and you may notice several thin rods sticking backward into the airflow. They look almost ridiculous next to the machine carrying them. From a terminal window, they are easy to mistake for loose hardware or some kind of sensor. They are neither. They do not move or flash. Most passengers will never know they are there. They do not create lift. They are not antennas. And on an aircraft weighing tens or even hundreds of tons, they seem far too small to matter. Yet engineers choose their position, number, spacing, and shape very carefully. A part this small would not be there without a reason. So why does a machine built to cross the sky need these tiny whiskers along its wings and tail? Let's get into it right here on Small Things. An airplane can charge itself just by flying. The answer begins with something passengers cannot see. An airplane can become electrically charged simply by flying. It is not moving through empty space. Its skin can meet rain droplets, snow, ice crystals, dust, and countless particles suspended in the atmosphere. At several hundred miles per hour, those contacts happen again and again across a very large surface. Repeated contact and separation can transfer or separate electrical charge. Over time, an imbalance can build across the aircraft. The important point is not one dramatic collision. It is the accumulation of countless small interactions as the airplane keeps moving through the atmosphere. Aviation has a name for this: precipitation static, usually shortened to P-static. The name is a little misleading. Rain is only part of the story. Snow, ice crystals, dust, and other atmospheric particles can produce the same general effect under the right conditions. Most passengers never notice any of it. There is no dramatic flash from the cabin, no warning light announcing that the skin has picked up charge. The airplane simply keeps flying while that electrical imbalance grows in the background. Accumulating charge is not automatically dangerous. The real trouble begins when it starts leaving the aircraft in places engineers did not choose. The real problem is the noise. Modern airplanes depend on electrical signals that can be tiny compared with the machine carrying them. Communication radios, antennas, navigation receivers, and other avionics all rely on clean signals. Unwanted electrical discharges from the airframe can create radio frequency interference. To a pilot, the result may sound surprisingly ordinary: crackling in the headset, bursts of static, or a weak transmission becoming harder to understand. Under some conditions, navigation reception can also be affected. Imagine trying to catch a faint radio call in rough weather while the airplane itself is adding noise to the signal. The problem does not require a radio to fail. A discharge only has to add enough unwanted energy to make a weak signal harder to separate from the noise. Aircraft already use electrical bonding to keep major conductive parts at similar electrical potential. That reduces unwanted voltage differences between structures and gives charge a more predictable path through the airframe. But bonding cannot make the charge vanish. It can help control where electricity moves inside the aircraft. Eventually, however, the excess charge still has to reach the surrounding air. That missing piece is what the tiny rods provide. That is what the whiskers are for. Those thin rods are static dischargers, more commonly called static wicks. They do not suck electricity from the airplane, and they do not connect it to the ground. Instead, they provide preferred discharge points. Without carefully chosen exit points, charge may leave from other parts of the aircraft where the resulting radio interference is less predictable. Static wicks encourage that release to happen at locations selected for the job. The simplest way to think about it is this: the static wick does not eliminate the electricity, it gives the electricity a better exit. That is why a part only a few inches long can matter on an aircraft thousands of times larger. Its job is modest but precise. It does not power anything, steer anything, or sense the air. It gives an invisible electrical process a place to happen more predictably. away from locations where an abrupt discharge could create more interference. The function is now clear. The stranger question is how such a small rod can influence charge spread across an entire airplane. Why a sharp point changes everything. The answer is hidden in the shape. Electrical charge does not behave the same way across every part of a conductive surface. On a broad, smooth area, the electric field is more spread out. Near a sharp edge or narrow tip, it becomes much more concentrated. That is why a static wick is thin and ends in a very small point. The point is not sharp because engineers wanted a needle. It is sharp because electricity behaves differently around sharp geometry. As the electric field near the tip becomes strong enough, it can begin to ionize some of the surrounding air. Those newly charged particles make it easier for electrical charge to move away from the aircraft. This process is called corona discharge. It is important not to picture a tiny spark repeatedly snapping from the wing. A spark is a sudden electrical breakdown through the air. Corona is more gradual and remains concentrated around the region where the electric field is strongest. Think of the difference this way. Spread the same electrical effect across a broad surface, and nothing is especially concentrated. Give it a very fine tip, and the local field becomes much stronger. That allows discharge to begin more readily at a location engineers chose in advance. So the static wick is not clever because it contains some complicated machine inside. Much of the trick comes from something simpler, its shape. Here, geometry itself becomes part of the electrical system, and once shape matters, location matters too. Why they are at the back of the wing. That same principle helps explain where engineers put static wicks. They are commonly found along trailing edges, wingtips, tail surfaces, and other extremities rather than scattered randomly across the aircraft. Charge does not distribute itself equally across every part of the airframe. Tips and edges are especially useful places for stronger electric fields to develop, so they make natural locations for controlled discharge. These are also regions where airflow leaves or separates from the aircraft. Another reason trailing edges and extremities are useful places for the job. Placement can also keep discharge activity away from areas where it could create greater interference with sensitive radio equipment and antennas. There is no universal pattern that works for every airplane. The number of dischargers, the spacing between them, and the exact surfaces on which they appear can vary with the aircraft's geometry, construction materials, bonding arrangement, antenna layout, and electromagnetic characteristics. Those little rods are not scattered wherever there happens to be space. Their location is part of the electrical design of the airplane, and their pointed shape leads to one of the easiest mistakes to make about them. No, they are not miniature lightning rods. A pointed object associated with electricity creates an obvious assumption it must be there for lightning. But static wicks do not prevent lightning strikes, and they are not the aircraft's primary lightning protection system. An airplane can have perfectly functioning static wicks and still encounter lightning. Lightning is a much larger engineering problem. Aircraft rely on broader protection measures such as conductive structures, electrical bonding, shielding, protected systems, and engineered current paths to deal with the enormous currents involved. Static wicks address something else. A lightning strike is a sudden, high-energy electrical event from the surrounding atmosphere. P-static builds gradually as the airplane moves through particles that exchange charge with its surfaces. A lightning strike is something the airplane must survive. P-static is a condition it manages during flight. The difference matters because the two problems demand very different solutions. Static wicks belong to the quiet, continuous side of that electrical design, not the dramatic one. Not every static wick is the same. Once you know what they do, another detail becomes easier to notice. Static wicks do not all look identical. Some designs use metallic conductive elements. Others can incorporate carbon-based materials. The exact construction depends on the aircraft and its electrical characteristics. Whatever the material, the goal remains the same: provide an engineered discharge path while keeping radio frequency interference as low as practical. So even though they look like simple rods, they are not generic accessories that can be swapped around without thought. Their simplicity is only on the outside. What if one of them breaks? Static wicks live in a harsh place. They sit outside the aircraft, exposed to airflow, weather, vibration, contamination, and ordinary wear. Over time, one can loosen, break, become damaged, or lose effectiveness. That is why their condition matters during maintenance. Tiny exterior parts that passengers may never notice can still affect how well the aircraft manages piece static. A missing or damaged wick does not automatically make an airplane unsafe, but it can reduce the aircraft's ability to control piece static as intended. In the right atmospheric conditions, that can make radio interference more likely. Its failure is usually not dramatic. That is exactly why it is easy to underestimate, which brings us back to the tiny rods we started with. The clever part is not that static wicks somehow stop static electricity from existing. An airplane cannot avoid every raindrop, ice crystal, dust particle, or atmospheric condition that can create charge. So rather than trying to prevent the problem from forming, engineers control what happens next. Sometimes good engineering does not eliminate a problem. It simply gives the problem somewhere safe to go. When the system works, there is no spectacle. The pilot may hear nothing unusual, and the passenger sees only a few thin rods at the edge of a wing. The next time you notice those tiny whiskers along a wing or tail, you are looking at a small part quietly managing an invisible problem across an enormous machine. If you enjoy discovering the hidden purpose behind ordinary-looking details, subscribe for more stories from the world of simple things.